I welcome you all to this fourth lecture on the title Sequence and Series. To begin with, let us recall a definition we made at the end of previous lecture, namely the definition of a series. Given a sequence an, consider the expression a1 plus a2 plus a3 plus etc. This expression is what we mean by a series associated with the sequence an. By this time, the distinction between sequence and series should be clear. Sequence is an ordered list of numbers and series is a sum. Let me remark also that while considering the expression, namely sum of infinitely many numbers a1 plus a2 plus a3 plus etc., we are not bothered whether this expression finally represents a real value or not. Those questions will be answered or discussed in other notions connected with series. By a series, we just mean this expression or a formal sum. a1 plus, a2 plus, a3 plus, etc. Also, let us note that by definition, a sequence is a function from a subset of non-negative integers. If that subset is finite, we get a finite sequence, so that in this collection of terms a1, a2, a3, etc., there will be only a finite number of terms. If we deal with a function from a subset of set of non-negative integers, where the subset is an infinite subset, correspondingly we may get an infinite sequence, and in that case the series will be a infinite sum. In short, what I would like to convey is the following. If sequence an is finite, the corresponding series is finite. If sequence an, let us write n equal to 1 to infinity, is infinite, then corresponding series is infinite. Note that a finite series, which may look like a1 plus a2 plus etc. plus an, is just sum of finitely many real values. Hence, it always represents a finite real number. whereas an infinite series a1 plus a2 plus etc. may or may not represent a finite real number. Let us recall the notation we introduced for the sake of simplifying sum, namely the sigma notation. a1 plus a2 plus etc. plus an can be written using sigma notation, summation I is equal to 1 to n. Analogously, a series a1 plus a2 plus etc. can be represented using sigma notation as follows. a1 plus a2 plus etc. is equal to summation I is equal to 1 to infinity. This infinity in the upper limit is used to denote that the series that we deal with is infinite series. Having defined what is a series, let us proceed with one more definition. Consider the sequence an. Let us say n equal to 1 to infinity. We construct a new sequence out of the given sequence an. And that sequence I call as Sn, as follows. The first term S1 is same as A1. The second term S2 is same as sum of first two terms of the given sequence. S3 is A1 plus A2 plus A3. So on, Sn is A1 plus A2 plus etc. plus an, so on. Sn can be denoted using sigma notation. Let us recall, you are given with a sequence an, we construct a new sequence Sn where the terms are defined as follows. The sequence Sn is called sequence of partial sums of the series summation an n is equal to 1 to infinity. We are making the definition of sequence of partial sums. Remember, given a sequence, we have corresponding series expressed as summation n equal to 1 to infinity an. And for this series, how do we define sequence of partial sums? To define sequence of partial sums, we construct a new sequence sequence Sn, where S1 is A1, S2 is A1 plus A2, and so on. Is the definition clear? Now the question is, what is this definition for? Recall that when we deal with sum of infinitely many real numbers, A1 plus A2 plus A3 plus etc., we cannot keep on adding and see what comes out. Then how do we assign a definite meaning for an infinite sum A1 plus A2 plus A3 plus and so on? The answer is the following. We construct sequence of partial sum Sn. The nth term, namely Sn, in the sequence of partial sums is called nth partial sum. Sn is called nth partial sum. Remember, nth partial sum Sn is A1 plus A2 plus etc. plus An, which can be found by normal addition. Next, what we do is we observe what happens to Sn as n becomes larger and larger. That is, we observe convergence or divergence of Sn. Sequence Sn. If the sequence of partial sums Sn is convergent, then we say that the series is convergent, and if the sequence of partial sum is not convergent, we say that the series is divergent. Let us make it as a definition. For a given sequence An and corresponding series summation An, n is equal to 1 to infinity, construct sequence Sn called the sequence of partial sums. If this sequence of partial sum is convergent, that is, if there exists a real number capital L such that as you progress towards the end of the sequence Sn, the terms are becoming close enough to this L, then we say that summation An is convergent. Otherwise, we say summation An is divergent. Intuitively, you can understand like this. instead of adding A1 plus A2 plus A3 plus so on and seeing what comes out, which is not practical, we first find sum of first n terms, that is we find Sn, nth partial sum. We observe a pattern and see if Sn becomes close to some number L as n becomes larger and larger. If yes, that number is taken as the sum of this infinite series. In notation, if limit n tending to infinity Sn is equal to L, meaning the terms of sequence Sn become close to L as n becomes larger and larger, then we say summation an is equal to same L, and that L is taken as the sum of this infinite series. Instead of keep on adding and observing what comes out, we observe what happens to partial sum as n becomes larger and larger. And the sequence convergence is used to say whether the series is convergent or not. Given a series, we form a new sequence called sequence of partial sums, and if the sequence of partial sum is convergent, we say the series is convergent. Intuitively, that means this infinite sum ultimately gives rise to a finite value. When we say a series is convergent, what we mean is the series is summable, in the sense after adding all these infinite number of real values, we will come up with a finite value. So, to sum up, how do we assign a definite meaning for infinite sum? Answer is, it is through convergence of sequence of partial sums. The convergence word is attached with both sequence and series. Convergence for a sequence is something that says what happens to the sequence as you progress towards tail end of the sequence. And convergence of a series is something to say whether the series is summable, means after adding all the terms whether you will come up with a finite value or not. Now, we got a definite meaning for an infinite sum, a1 plus a2 plus etc. What does it mean? How do we attach a number to it? That depends upon whether the series is convergent or not. And the series is convergent or not depends upon the convergence of sequence of partial sums. We may not enter into rigorous study of convergence of sequence and series, but then let us have some examples to understand how do we say whether a series is convergent, or how do we see whether an infinite sum ultimately give rise to a finite value or not. Let me give you an example. So, the given series is 1 plus 1 by 2 plus 1 by 4 plus 1 by 8 plus etc. 1 by 16 plus etc. I hope you can observe a pattern. It is powers of 2 in the denominator, 2 power 1, 2 square, 2 cube, 2 power 4 and so on. Just to make the notations clear, understand that this series summation an arises from the sequence 1 by 2 power n is equal to 0 to infinity. First term of that sequence is 1 by 1, that is the first summand here. Second term of the sequence is 1 by 2 power 1, that is the second summand in this infinite sum and so on. Now, the question that we want to answer is whether this infinite sum represents a finite value or not. In other words, whether this series is summable or not. More technical word is whether this series is convergent or not. To see this, as we developed in the theory, first we have to see sequence of partial sum. So, let us find sequence of partial sum for this given series. The first partial sum, namely S1, is A1, which is 1. The second partial sum, S2, is A1 plus A2. Here it is 1 plus 1 by 2. Observe that S2 can be found by normal addition. Third partial sum, S3, is A1 plus A2 plus A3, which is 1 plus 1 by 2 plus 1 by 4 and so on. S2 is 3 by 2, S3 is 3 by 2 plus 1 by 4, which is 7 by 4 and so on. Sn, the nth partial sum, will be 1 plus 1 by 2 plus 1 by 3 plus etc. plus 1 by n, so on. To answer the question whether the given series is summable, convergent or not, we have to see this sequence Sn, n is equal to 1 to infinity, is convergent or not. Let us try to observe a pattern. See that S1 is 1, S2 is 3 by 2, 1 plus half, S3 is 7 by 4 and so on. It is bit involved, but still with a careful observation it can be seen that there is a pattern and Sn, the nth term, will be 2 power n minus 1 by 2 power n minus 1. First term is 1 second term in the sequence of partial sum is 3 by 2, third term is 7 by 4 and so on, nth term is 2 power n minus 1 by 2 power n minus 1. It's bit involved to see an expression for Sn like this. However, let us try to do it in a slightly different manner. Consider a unit square. Imagine two copies of unit square are pasted like this. The area of this one is 1. Let us halve the second unit square. Area of this first half portion is 1 by 2 and second half portion is 1 by 2, and the second term in the partial sum S2 can be attached with the area of first square plus half of the area of the second square. So, S2 is total area, which is 2 minus half. This portion is missing. You can see that S3 is 1 plus 1 by 2 plus 1 by 4, which is area of the first unit square plus area of half of the second unit square, and again you have to add half of the remaining half. This is 1 by 4. This is S3. So, S3 is 1 plus half plus 1 by 4, which is actually total area minus 1 by 4. Total area is 2 minus 1 by 4. This portion is missing. Similarly, in S4, you can see that S4 is sum of 1 plus 1 by 2 plus 1 by 4 plus 1 by 8. That is total area 2 in which 1 by 8 is missing, and so on. Now, you can observe that S1 is 1, S2 is 2 minus half, S3 is 2 minus 1 by 4, S4 is 2 minus 1 by 8 and so on. Observing the pattern, Sn will be 2 minus 1 by 2 power n minus 1. That is what we got. Sn is equal to 2 power n minus 1 by 2 power n minus 1, which is 2 minus 1 by 2 power n minus 1. Thus, for a given series, namely 1 plus 1 by 2 plus 1 by 4 plus 1 by 8 plus etc., the sequence of partial sum Sn, n is equal to 1 to infinity, is given by Sn is equal to 2 minus 1 by 2 power n minus 1. Observing this sequence of partial sum S1, S2, S3 and so on, it is not hard to see that as n increases, terms of the sequence Sn become close to 2, because as n increases, this n minus 1 is a large value. So, 1 by 2 power a large value, this goes to 0. So, as n becomes larger and larger, Sn become closer enough to 2, which we write as limit n tending to infinity Sn is equal to 2. Informally, what we have observed is that the sequence of partial sum is convergent and the limit of the sequence of partial sum is 2. Recalling the definition we made for convergence of a series, it should be clear that since the sequence of partial sum is convergent, the corresponding series is convergent. So, 1 plus 1 by 2 plus 1 by 4 plus etc. is convergent. That means this infinite sum ultimately gives you a finite number. And what is that number? 1 plus 1 by 2 plus 1 by 4 plus etc. is the limit of the sequence of partial sum, that is, it is 2. Thus, in this example, for a given series, we constructed the sequence of partial sum. We observed a pattern. We could write nth term of sequence of partial sum in terms of n. Sn is equal to 2 minus 1 by 2 power n minus 1. Since we could write Sn in terms of n, we could observe what happens to Sn as n becomes larger and larger. And we could see that as n becomes larger and larger, the terms of the sequence of partial sum comes close to 2, and that too is treated as sum of this infinite series. If you observe this procedure, it should be clear that the success of this depends upon whether we could express Sn in terms of n or not. In this particular example, though it is bit involved, we could observe that Sn can be expressed in terms of n, and through that we could see what happens to Sn as n becomes large enough, and through that we could find whether the given series is summable or not. However, it may not be always possible to find sequence of partial sums in such a manner that Sn is given in terms of n. Thus, testing whether a given series is convergent, meaning testing whether given infinite sum finally gives a finite value or not, is bit involved task. Let us not enter to the details of how to check whether a given series is convergent or not, etc., etc. In fact, it is not always advisable to find the sequence of partial sum and then check whether the sequence of partial sum is convergent or not. We may have to rely on some easy techniques. Let us not enter into those details. To sum up, we should have a clear distinction between sequence and series. Sequence is ordered list of numbers, and series is a sum. It is sum of terms of a sequence. Since we may have to deal with sum of infinite number of real numbers, and since it is not straightforward as to deal with sum of finite number of real numbers, we have to resort on certain notions regarding sum of infinite number of real numbers, and the notion is convergence or summability, and summability or convergence of series is achieved through convergence of sequence. Thus, the notion of convergence of a sequence help us to break down the narrow confine of sum of finite numbers. We can also deal sum of infinite number of real numbers using the convergence of sequence. Next, we shall discuss some special kinds of sequence and series where there is some relationship between terms of the sequence or the series. In that context, we will first discuss what is called as arithmetic progression. Let us observe some examples. Consider the sequence 2, 4, 6, 8, 10, etc., 2n, etc. In fact, it is the ordered list of even numbers. Consider the sequence 5, 10, 15, 20, 25, etc. Consider the sequence 4, 3, 2, 1, 0, -1, etc. If you observe the first sequence and ask how the sequence progress, we can see that the difference between the second term and the first term, namely 4 and 2, which is 2, is same as difference between the third term and the second term, 6 minus 4, which is 2, which is again same as the difference between fourth term and third term. Similarly, in the second example, difference between second term and first term is 5, which is same as difference between third term and second term, which is again 5, which is same as difference between the fourth term and third term, and so on. Same is the case with third example, where difference between second term and first term, namely 3 minus 4, is -1. Difference between third term and second term, namely 2 minus 3, is -1, and so on. In these type of examples of sequence, the difference between two consecutive terms remains the same. Such a sequence is called arithmetic sequence or arithmetic progression. A sequence in which difference between two consecutive terms remains the same. Is called an arithmetic sequence or arithmetic progression. AP in short. In symbols, we can define an arithmetic progression as follows. A sequence an, n is equal to 1 to infinity, is called arithmetic sequence or arithmetic progression. Let me write AP if an plus 1 is equal to an plus d for every n greater than or equal to 1, where d is a real number. N plus 1th term is obtained from nth term by just adding d. This is true for every n. So, second term is first term plus d, third term is second term plus d, and so on, where that d remains same. Here d, which is the constant difference between two consecutive terms, is called common difference. So, in the example we started with, 2 is the common difference. In the second example, 5 is the common difference, and in the third example, minus 1 is the common difference. Let us note that a arithmetic progression with first term as a and common difference as d can be written as a plus d, a plus 2d, and so on. Thus, a plus d, a plus 2d is the general form of an arithmetic progression with first term a and common difference d. Observe that when we have three terms in the AP, a plus d, a plus 2d, there are two common differences that you can work on. Difference between second and first, difference between third and second. In fact, they will be same. However, if there are three terms, we can work with two common differences. If there are 5 terms, you can see that you can work with 4 common differences. If there are n terms, there are n minus 1 common differences that you can think of, and the nth term can be obtained from the first term by adding this n minus 1 common differences. Do you see it? The third term can be obtained from the first term by adding 2d. And what is that 2d? 2 common differences when we move from first term to third term. So, in general, the nth term of a arithmetic progression with first term A and common difference D is A plus n minus 1 into t. When we have to deal with n terms, we can have n minus 1 common differences, which when added to A will give the nth term. Let us observe some facts about arithmetic progression. First fact, if we add a constant to each term in an arithmetic progression, the resulting sequence is again an arithmetic sequence or arithmetic progression. That is, if we are given with an arithmetic progression an, n is equal to 1 to infinity, in expanded form a1, a2, a3 and so on, we construct a new sequence Bn, n is equal to 1 to infinity. How do we do that? Bn is the nth term in the given sequence plus d. Let me write d dash. That is, we consider a1 plus d, a2 plus d, a3 plus d and so on. And the fact is, if the given sequence a1, a2, a3 is an AP, that means the difference of two consecutive terms remains same constant, then the new sequence that we constructed remains to be an AP. That is, the difference between two consecutive terms in this new sequence will also remain the same. So, we can construct new APs from the given AP by adding constant with each term, same constant to all terms. We can continue with some more facts about arithmetic progression and some new types of sequences in the next class. Thank you.